Welcome back to the Deep Dive. Our mission today is pretty laser-focused. We're taking a deep, concentrated look at a single research paper that could be a huge step up in how we train advanced AI.
That's right.
We are diving into a novel training paradigm called Natural Language Actor-Critic, or NLAC for short. Now, when most people think of large language models, you think of asking a quick question and getting a single, polished response back.
Sure, like a Q&A.
Exactly. But the real cutting edge is what we call LLM agents. These are models that don't just answer, but they actively interact with an environment over a long horizon.
Right.
Think of an agent that has to navigate the web, or use complex coding tools, or handle a multi-turn, goal-oriented customer service dialogue. These things require real strategy.
And that's the key difference. LLMs are amazing at the single response task because at their core, they're just exceptional next token predictors.
Yeah.
But moving to those complex agentic tasks, where the model has to plan, say, 10 or 20 steps ahead, handle a tool failing, and keep a long-term goal in mind, that requires specialized fine-tuning. It needs to go way beyond basic supervision.
They need to learn strategy from consequence.
Exactly, from consequence.
And that strategic learning is where NLAC just completely shakes things up. We're going to see how this technique fundamentally changes the currency of feedback for these agents, moving them away from, simple numbers and toward rich, strategic, explanatory language.
Okay, so let's maybe unpack the baseline first, where we are today.
Good idea.
So if you want an LLM to become a successful agent, you generally start with supervised fine-tuning. You're basically teaching it the format of good actions, and then you shift to reinforcement learning. This usually involves policy gradient methods like proximal policy optimization, PPO, or maybe GRPO. The LLM is trained to generate high-level reasoning right alongside the actual actions. It's a pattern you see in techniques like React.
But if you've spent any time at all looking at RL applied to large language models, this whole process is, it's notoriously brittle.
Oh, absolutely.
Traditional RL methods bring in these two enormous stability and efficiency issues, especially when you apply them to complex long-horizon tasks, particularly where the action space is just vast, like generating natural language.
The first major pain point, and it's a big one, is data inefficiency. These standard methods are strictly on policy.
Okay, what does that mean in practice?
Well, think of it this way. Your LLM agent just ran a long 20-step task, and it failed at the very end. It learns a single tiny lesson from that failure.
Right.
In an on-policy system, to learn the next lesson, the agent has to discard that entire 20-step history. It just throws it away and has to sample a brand new, full, expensive 20-step trajectory from its new, slightly improved policy.
Wow. So it's like having to burn your entire research library after you learn one new historical fact.
That's a perfect analogy. You can't reuse past experience. You are forced to generate new, complete data sets for every single tiny improvement, which makes training just agonizingly slow and expensive.
And that inefficiency problem is then compounded by the second major issue, right? The weak training signal.
Exactly. The what's often called the sparse scalar reward problem. In a task with a lot of steps, the agent usually only gets a simple 1 for success or a 0 for failure right at the very end of the whole thing.
So no partial credit.
And no partial credit. If you complete a 30-step goal, great, you get a 1. If you fail at step 29, you get a 0. And then the model has to somehow figure out whether that failure was caused by a slight misstep at step 29 or a massive strategic blunder way back at step 5.
I see. And that difficulty in assigning credit to the right action in a long sequence is why these agents struggle to develop robust, generalizable strategies. So we have the problem instability and this desperate hunger for data. What do the researchers propose to solve it? This is where NLAC introduces its core innovation, the critic that speaks English.
Yes. NLAC presents a completely novel actor-critic framework, but the shift isn't just algorithmic. It's fundamental. They replace the traditional value function, which just outputs a scalar, a simple number representing expected future reward, with a generative LLM critic that outputs rich natural language. It doesn't tell you how much your move was worth. It generates a detailed textual critique of your action.
Okay, here's where it gets really interesting for me, because it leverages the true power of these models. In classical RL, if an action is suboptimal, the policy has to discover a better one through, randomized search and trial and error, guided only by that abstract number.
Right, it's fumbling in the dark.
Exactly. But if the value function is delivered in the form of a linguistic explanation, a paragraph telling you exactly why your decision was strategically flawed, the LLM policy can just bypass all that random chance. It can immediately understand how to improve because the critique is in the same language it uses to reason.
It's a much richer and more actionable training signal.
Way more.
And this framework, it falls under the paradigm of natural language reinforcement learning, or NLRL. But NLAC had to overcome a huge technical barrier that made earlier NLRL attempts pretty impractical.
What was that?
Well, those methods required the system to basically list out all potential subsequent actions and environment transitions to calculate the best textual critique.
Which, when you're dealing with an LLM, is just impossible.
Impossible. An LLM's action space is combinatorial. I mean, every subsequent token choice just explodes the number of possibilities. You can't list out every valid conversation or every possible tool call sequence. The number of paths is functionally infinite.
So NLAC had to find a scalable way to generate that high-quality textual critique without that kind of exhaustive search.
Exactly. And this brings us to the mechanics. This is really the deep dive part. How do you actually engineer a talking critic that is both scalable and, theoretically sound?
Right. The whole NLAC system, both the actor and the critic, is built on the same underlying LLM. They're just given different prompts to follow. So let's look at the first main stage, policy evaluation. This is training the language critic.
Okay.
The ultimate goal here is to generate that detailed textual critique, which they call QLSS, is a life. It has to assess the optimality of an action and provide the explanation.
To do this, they introduce a component called the language successor model, or RMLers. This is a generative model that's trained to predict the text of the future.
So not a number, but a story.
A story. You give it a current state and an action, and ALM probabilistically generates a textual description of the anticipated future rollout. It's summarizing the most likely linguistic path the agent will follow next.
That's a fascinating reconceptualization of a successor feature. Instead of predicting how many times you'll visit a certain state, it's predicting the narrative of the task going forward.
It really is.
But here's the critical part that solves that data inefficiency problem we talked about earlier. How do they train this model without those expensive on-policy rollouts?
They use something called the language Bellman backup.
Okay.
This is the key piece of engineering that enables NLAC to train off policy. Remember the problem? Burning the research library every time you learn something new.
Right.
The Bellman backup solves this by adapting the concept of temporal difference learning. Conversationally, here's how it works. The agent takes a one-step sample from its vast existing old data, maybe a single failed step from last week's training run.
So it's recycling old data.
It is. It looks at the immediate reward and the next state from that one step. It then combines that real single-step observation with a bootstrap description of the future that the language successor model itself predicts. So instead of needing a full 20-step real-world rollout, they only need one real step, and then they use the model itself to predict the remaining 19 steps in text form.
You got it. Which means they can instantly reuse massive amounts of historical data. That's the definition of efficient off-policy learning. It's sample efficient because the agent only needs the first step of data, not the whole expensive trajectory.
Makes sense.
And once that successor model is trained to predict these textual futures, the critic uses another component called a language evaluator. This just aggregates multiple generated futures and summarizes them into the final, high-quality, actionable textual critique.
Okay, so that covers the critic. But how does the actor actually use that text to refine its behavior? We're back to that challenge. You can't calculate the best action by listing all possible sentences.
Right. So they solve this using a really powerful self-refinement mechanism. They define a separate, specialized refinement policy. Let's call it PIRE.
And it is prompted to process that rich textual critique. Based on the linguistic advice it's given, this refinement policy generates a refined, superior action.
So the textual critique provides the explicit linguistic intuition, why this was bad, and the refinement policy translates that intuition into a tangibly better action.
Exactly. Then the original base policy is updated toward this superior refined action using a distillation objective.
It's like a teacher-student model.
It is. The critic gives the teacher the refinement policy, the cheat sheet, and the teacher generates the perfect answer. The student, which is the base policy, then just learns to mimic that perfect linguistically informed answer.
And this entire process is trained off policy.
The whole thing,
Yeah.
leveraging all the benefits of that language Bellman backup we just discussed.
Okay, that makes the mechanics really clear. They've fundamentally transformed the training signal from a sparse number to a rich, reusable explanation. But the proof is always in the performance, right?
Always.
They tested this across some complex benchmarks, including mathematical reasoning, strategic dialogue like the 20 questions game, and these intricate customer service scenarios called TAW bench, which involve multi-step dialogue and tool use.
And the results were compelling. I mean, especially in the long horizon tasks where that credit assignment problem is most severe.
Right.
Using their QWQ32B model, the NLAC substantially outperformed traditional RL baselines. In the strategic dialogue of 20 questions, NLAC got a 32.1% win rate. That's a massive leap over PPO's 24.0%.
Wow.
And on the customer service benchmark, NLAC scored 0.59 compared to PPO's 0.47.
A 30% relative improvement in strategic success on 20 questions is huge. And just as importantly, remember that data inefficiency problem. Figure 4 in the paper confirms that NLAC converges in significantly fewer gradient steps than TPO.
Yeah, that's key.
It's not just getting better results, it's getting them faster. It's direct confirmation that text-based reasoning dramatically improves sample efficiency and speeds up learning.
And let's bring this to life with the qualitative examples, because that's where you really get the aha moment.
Yeah, let's do it.
Okay, look at the 20 questions example. The agent has successfully narrowed the unknown object down to a non-red fruit. The base agent, lacking strategic depth, just defaults to a linear search. It asks, is the object typically green in color?
A simple but strategically poor move.
Very poor. But the NLAC critic doesn't just say, that was bad. The language critique reads, optimality, no. Rather than linear search over plant types, the guesser should aim to divide the plant kingdom more broadly. Linearly searching through fruit colors misses key discriminators like taste and size.
That is profound. That is actual strategic advice.
It is, and it informs the refinement policy to immediately shift gears. The refined action it generates is the object commonly found in a fruit salad?
Which is a much better question.
So much better. That question is designed to broadly divide the potential category based on usage, not just color. It's demonstrating a learned, high-level strategy that a simple scalar reward alone could never teach.
And we see this same powerful strategic correction in that customer service task. The user asks to modify a couple of exchanges. The base agent successfully handles the first item modification and immediately calls the database tool to update the order.
It did its job, but only partially.
Right.
The problem is that in that environment, calling the tool often locks the database, which makes any subsequent modifications impossible. The base agent violated the long-term policy goal without even knowing it.
Until the critique steps in.
And the textual critique identifies this latent failure mode. It says, optimality, no. The action does not anticipate the need for subsequent modifications. When the user requests to modify another item, this will fail, as it is no longer modifiable.
That is the level of foresight we want in an agent. The refined action, informed by that strategic critique, immediately corrects the plan before the tool call is even made.
It prompts the agent to say, I should confirm with the user that no other items need modifications before attempting the database transaction.
It avoids a policy failure based entirely on a linguistic prediction of future consequences. That is a massive leap in robustness.
It really is.
So what does this all mean for the future of LM agents? NLAC has successfully solved this dual problem of LLM-RL training. It's moved the paradigm away from sparse numerical feedback and reliance on expensive on-policy sampling
toward rich, explanatory, off-policy, textual feedback.
And that combination makes these agents faster to train, significantly more robust, and fundamentally better at long-horizon, complex strategic tasks involving dialogue and tool use.
And we should note, this success isn't just some clever hack. The theoretical analysis in the paper confirms that under reasonable assumptions, the textual values generated by the language critic do correspond monotonically to the true optimal scalar Q function.
So it's grounded in theory.
The complex textual reasoning is firmly grounded in classic reinforcement learning theory.
Okay, that's fascinating.
And this reliance on the generative language critic to define the path to optimality, it raises a really important question for you to mull over.
Go on.
NLAC is incredibly effective, but the researchers noted that they optimized the actor using only distillation, just mimicking the refined action.
Right.
What if the textual critique could be used not just for refinement, but to reliably extract a generative scalar value, a numeric measure of optimality? Could a hybrid algorithm be built? Could we combine the stability of this off-policy language learning with the sophisticated continuous optimization of traditional methods like PPO to potentially create the ultimate universal trainer for the next generation of LLM agents?